Now let's have a huge round of applause for Marcin and let's get started.
The clicker. Welcome, folks. One of the big challenge of giving talks to such a group of people is that I need to keep you focused on the talk. Each one of you has a phone in your hand, means that I have about 30 seconds per each slide to keep you entertained, and hopefully I will, before your mind will switch, let's check something on the phone. So, I hope this will be a fast and quick talk that will teach you something about zk and about the exciting future. So, without further ado, let's go. So, first, fast zk is here. Yay! Let's go. Okay. You know, things that we've been talking about. Zero knowledge since 2012 when it started as this side project, this side math project. We've been improving and improving over this, and now it's fast. Now we can do all these things, but where's the excitement? Should be celebrating about it. It's like lunar landing for Ethereum, but it's quiet. So why is that? Some people are talking about it. There's some excitement, but it's still on the low level. It still did not reach the Ethereum masses. One of the reasons might be that many of us here don't fully know what it means. People know, like, yeah, there is some zk something, there is some complex math. Yes, cool, Ethereum is going towards zk, people are talking about it, there will be some risk, VMs, fine, we'll figure it out when it gets there. So during this talk, my challenge, my mission, is to teach you just a little bit, for you to get enough excited, so that you understand the possibilities, you understand the new things, the new frontiers that it opens. Not only for Ethereum, but also for other startups, for other ideas that can be now built on top. Things that were really not possible a couple years back, now are. As this is a short talk, this is what zk is. You take a computation, you do a polynomials, and you do a proof. In the past, I really tried to teach people zk in half an hour. I failed. I mean, the way it looked is like, I've been doing this. People were like, and then nothing. So, 3 things I did. I actually did a children's book. We'll talk about this later, some Twitter posts, whatnot. So here, I will not try to explain the detailed math. It's fascinating, by the way. This is actually the way when you can say, hey, I'm doing crypto, and I'm doing real math. This is not this scammy thing, it's like real math. So if you do have time, one thing I encourage you is to try to learn a little bit how zk works. But in the current world, with zk being fast, this is equivalent of learning how exactly CPU works. If you're a computer scientist, if you're passionate about this, yes, you can, but you don't need that in order to use the computer. So instead, what I want is I want to give you a little bit of intuition of what zk is, how you can use it, and go beyond. And again, if you find it fascinating, by all means, please reach out. We can talk about how it actually works under the hood. But for now, let's focus on the intuition. Let's focus on how to use the computer, not necessarily how it's built. So if you were to sum up zk intuition in one slide, this is this. Hashing, that I hope all of you are familiar with, if not, hey, blockchain 101, is the way of, quote-unquote, compressing data. It's not really compressing, you cannot decompress it, but like, for a given amount of data, you create a one hash, done. zk proofs, the way you can explain it in 2 seconds is like compressing computation. It sounds strange when you hear it about it. You're like, what do you mean, computation? But the same analogy, the way how you say this hash can represent petabytes, exabytes of data, the same way you can say this zk proof can represent hours, thousands, millions of hours of computation. Same logic. Now, what does it mean a little bit in practice? This means that imagine Łukasz had a program that he shared with us. It's an open source program. And he said, Marcin, I put some secret inputs in there, and I got some output. We don't know what went in, but we know that he generated something. Now, he can generate the proof out of that. He can generate a small proof that will contain this output and will prove to everybody here that, yes, he actually had some inputs to this program. The small concept means that he can run something for hours, for days, come up with the result, and then create a small proof to show this. So again, this is the magic of what I'm calling compressing of the computation into the proof. Of course, today we use it where? Mostly in case of different L2s, different zk coprocessors, as a way of proving that the whole L2 computation, these thousands and millions of transactions, were actually valid, and boom, we just send a small proof to Ethereum. Now, the problem we had was how fast zk is. If I was giving this talk 4 years ago, I would be talking about clusters of super powerful GPUs in order to be able to compute a very small specific path. When we were doing provers 4 years ago, they literally were like measured in kilohertz. How many not only transactions, how many operations can do per second per GPU, whatnot. Within 4 years, thanks to, by the way, a lot of work from many, many people, from many, many companies, because this is the beauty of blockchains, we are building in open source, meaning people can build on each other. And this allowed us, as a community, to jump from 10 kilohertz to 13 megahertz right now on a single GPU. So what does it mean? This means that at home, on a single GPU, and again, now we know how to do things in parallel, you can basically run the 286 machine that will be live proven. Exciting? Yeah. Good. Some of you did run 286 in the past, so we know how exciting it was to get a machine like this. So everything you've been running 30 years ago, now you can do with zk proven. This means it can be straight proven on Ethereum. But more seriously, what this means is that on top of that, zk proofs can also be folding. You can use the machine to verify the zk proof that you generated before. This is a trick that we could not do 30 years ago, meaning that now you can actually run hundreds upon thousands of these, generate 1,000 proofs, and then put them on another machine to verify it, then generate a proof of this verification, then verify it, then verify it, then verify it, you end up with one. This kind of going deeper allows you to, in theory, prove a lot of computations, even without having, 13 megahertz right now at your desk. So, what does it mean? Now that you know that, hey, we are on 286 level, and again, if we keep going like this, of course, this will slow down a little bit, we're going to reach, 100 megahertz level, gigahertz, we'll see. So what you can do, the very first thing that will impact most of people here, at least if you're a developer, is we'll finally be able to go to sane languages. Don't get me wrong, Solidity, great. The same way how we were doing DOS development back in the days. Single-threaded, very careful assembly inserting to optimize this, to doing magic to fit on a diskette, 144 megabytes just to, compression, whatnot. We're doing these things right now on Ethereum because we have to. With zk, what you're able to do, and you see more and more people pushing towards this, you will be able to run RISC-V instructions. This means, RISC-V is like simplified x86, whatnot. This means that you are able to write Rust code, write C++ code, Java code, whatnot, compile into this and run. This will remove the problem of us having to squeeze all the computation to run on this, let's call it DOS box of Solidity right now, and go to really unblocked developers. Because think about how much faster you are, let's say, writing Rust code than writing, Solidity and whatnot. So this will open up the world to many, many developers. But that's not all. Because now, with zk, the fact that we're able to prove so much cycles means we can be wasteful. Faster. Means that we don't have to think again about like every single cycle. We can be like, rather than re-implementing everything in Solidity. Imagine your task was to take some business logic that some insurance company is doing and put it on chain. What you would have to do today is sit down, probably with ChatGPT, and start rewriting it painstakingly into Solidity to make sure you didn't screw up. With zk, what you're able to do is you're able to take that code, whatever Java magic is in there, you don't want to look, compile it into RISC-V, and just run it. Sure, you might have to do some patches like on the inside and outside, but you don't have to mess with the core code. This will allow us to be so much faster in moving the world on chain. Because again, we'll not rebuild it, we'll just move it. But zk is not only the succinctness, it's not only the compression of computation, it's also the ability to choose what is public, what is private. Blockchain is amazing, great, but everything has to be public right now, because that's the only way how we can make sure that the computation is valid. With zk, if you remember the slides before, we said the input is public, is private. So you can choose what you're sharing. You can be, okay, this part will be shared, this part will be private. This gives a lot of possibilities. This opens up the world to scenarios where you want to prove to someone that you did the computation, but you don't want to share all the info. And we'll talk about examples in 2 slides. Sorry, in 1 slide, I lied. So some concrete ideas what you can do just from listening what I've been talking about. Think about data. Have hospitals, lawyers, banks, they have data that they cannot share. At the same time, there are plenty of places where they want to run computation over this data. Hospital claiming that they have 2,000 patients with cancer of a given type. With zk, they can actually run this over this. Lawyers saying that, yes, they have a given deals. With zk, you can actually take the take the PDF parser code. There are plenty of these that actually can verify the PDF signatures, can extract the data, you can do all this computation. They can do all this computation on their GPU. Just send the proof to Ethereum. And you know they did that. The same thing with like all the things with R&D, clinical studies, verifiable research. How many times researchers say, yeah, I've been running this experiment for many, many days, and here's the result. And by the way, to rerun it, please get 1 million GPUs, and off you go. Such thing, okay, with 30 megahertz, they will not be able to do that yet, sorry, but like for smaller cases, they will be able to. They'll be able to, I run all this research, here's the zk proof. I'm not sharing with you the inputs, that's kind of my still, let's say, my university secret, but here's the proof that I actually did that and I actually got the results I wanted. And there are many, many, many more cases, including some things like, hey, what's the data provenance? Who generated this image? Was it GIMP? Was it ChatGPT? We don't know. You don't know. I know. But how can I prove to you? Today, I don't have it. In theory, with this, I could show you a zk proof that, hey, I actually run the GIMP, I put some movements into it, and this was the result. Done. This was ChatGPT, by the way. I was too lazy to use GIMP. And last but not least, this is the thing that will come in the future as we get more and more performance. It's basically machine learning model inference. The problem we're going to have very, very soon, we have it already, people don't notice yet, is many of the results we're seeing, people will be saying, machine said so. Your insurance was rejected? Sorry, sir, the machine learning model said that you were rejected. Your healthcare claim got rejected? Sorry, that's the machine. Over time, when we have technology like this, you'll be like, okay, fair, but can you show me the zk proof that you really run that model that your CEO publicly claimed is running with this data? Or did you just say no? So as you can see, future is very exciting because we're able to move from trust but verify to just verify. Able to just take the data. And now the mission I have for you is learn how to use zk. You don't have to know the details the same way as I said. You don't need to know the details of the CPU, how to use it. But learn the boundaries, figure out what type of new things that we did not think in the past could be now settling on Ethereum. What kind of proofs of real-world use cases you can now move onto ZK and then prove on Ethereum, because this will really unlock a lot of new technologies and a lot brighter future for Ethereum. So as I promised, but if you're interested in how ZK works, please, this is the Eli 5 book. I try to make it as simple as it gets. There are also some, let's call it Eli 12, Eli 15 slides in there. You'll see it on my old Twitter that try to explain you the details. This will allow you to say, I'm doing math, honey. Really am. This is really the crypto of the crypto part. So, and that's it. Thank you, folks.
There you have it, guys. I have to say, I do have this book from ECC last year, and it's a very interesting way to explain it. And my family even got it. I was like, this is the kind of stuff I do. And then like, oh, wow, this is pretty cool. And do we have any questions? Yes. Sorry.
Yeah, you mentioned that you can run pretty much any code written in, let's say, Java or whatever language you have. But I'm more interested in the architecture. Let's say that we have some code that is using some specific instructions that do not exist on RISC-V or are not purely 64-bit ones. So there's no clean translation to RISC-65. How is it handled, or is it just not possible to run them?
You have two options. Option number one, if you're lazy, you try to put some shim to compile it to RISC instructions. Yes, some of them will be very slow, but you kind of do a transpiler, whatnot, to end up with RISC-V. Now, if you really want to be using a different instruction set, this means, oh, we need to talk, dude. You have to actually go very deep into these things and write your own custom circuit to do this. So kind of depending on your needs, I would definitely start with option number one, meaning transpiling whatever you have into RISC-V, running it potentially at some computation cost, because this will be slower, right? Some larger sets, whatnot, but this will allow you to kind of get started. And then when you see like, okay, I really need this to be cheaper, then think about custom circuits for your instructions.
In some cases, in some edge cases, it could be even way faster, but it's because of how x86 handles like partial memory, right?
Yeah. So the reason why we as an ecosystem chosen RISC-V is that R stands for reduced. So we're lazy, right? We wanted to start with something that has as small instruction set as possible. But I'm guessing that as the whole industry progresses, probably in a couple of years there will be just x86, direct running for ZK.
That's not really going to happen because of how Fortress ANC and architecture works. It supports 32 bits, so it's not really going to happen on RISC-V unless someone wants to do it for themselves. But
it's open source, man. Try it.
Doing that. It's like going backwards to 90, right? It's not good that yeah, army for this, for this, and they're stick with it, which is based on power. We can also power value and very specific like do the construction for other AMD. But they still exist. That software is still in use. Yeah, right.
Okay.
Sorry, guys. We can have one more question.
Yes, practical question. When you are talking about RISC-V, which is basically just another VM, just like the VM today, what requires compression, to be available in the case of ZK to actually make this work? Why not just use RISC-V the way you used EVM today? What does the snark, or ZK as you call it, actually unlock?
So what's happening is like this. Imagine you compile your code to RISC-V, you were running it for 5 hours. Like your code requires 5 hours to run. And now if you try to put this into Ethereum transaction and run it on Ethereum, well,
Right. So basically, it is not the VM support itself; it's that you are opening the bounds of how much computation you're going to do. You're making this effectively gasless, and so on and so forth.
Yes, you're kind of able to run this yourself and then end up with a small proof that you can then verify on Ethereum, right?
Right. And the only thing that actually will burn gas is the verification of the proof that you post on chain.
Yes.
Okay.
I have also a quick question. I'm from like an academic PhD research background. How do you approach institutions and research to, let's say, prove? Because like I will tell you honestly, is when you go to talk with researchers, half the stuff they sometimes say is just a lie. And I feel like they would...
Only half?
Maybe not half. Okay, I'm maybe over-exaggerating, but they don't want to necessarily prove it because I feel like they'll get caught out because that's how kind of like research is. They just basically fight each other until someone
wins. Look, the way it works, and I'll use the example of, a great comparison here would be something, TLDR peer pressure. For example, the amazing work that L2Beat is doing for L2s, kind of being like, guys, please, you're red here, please improve. The same thing. Once the tools are there, would happen to researchers. Because once those conferences will start putting a small bar saying this proof, this thing is not verified versus verified, whatnot, then this will create the pressure for this to happen. But it's still going to take a couple of years because we have to go a lot further than just 13 megahertz.
Okay, awesome. We have time for one more question.
Yep, very quick one. When Airbender coming for zkSync?
It's already there.
No, I mean when the chain is being proven by Airbender and the proof of Airbender is posted on Ethereum.
So, if not for this conference, it will be literally today. But because I screwed up some things, it will probably next week, whatnot. We're in the process of deploying it, etc., etc. So, but very, very, very soon. But yes, one thing I did not mention is those 13 megahertz are coming from zkSync Airbender. If you Google it, you will find the GitHub repo that is as simple to use as I could have made it. Meaning you can actually take your small Fibonacci program examples from this and just create a proof and be a proud zk proof generator on your machine at home on your single GPU. As I said, it's an excuse for you to get a proper GPU at home and be, yes, honey, this is for work. 5090 recommended, but 3090 works too.
I didn't realize what time it was. We do have time for more questions.
Hi, Carol here. So yeah, fast zk is here. As you mentioned, Airbender being fast on the kind of home machine, potentially 5090. And obviously, as you also mentioned, the privacy is an important aspect. But when you mentioned privacy, you did mention mainly running it on a cluster of GPUs. Do you believe client-side proving is something that's gonna happen sooner? Is it not something that we do require for privacy? And is 5090 not steep enough for users to use as their kind of client side?
So one of the things I'm running at home, and this is kind of something that we'll be announcing more widely as zkSync, is what I used to call bank in a box. Meaning I started a small L2 network that's literally running on my machine at home on the 3090. Yes, it takes 20 seconds to generate a proof. But for a small, that's what I'm calling it, we're calling it Prividiums, for a small network, that's kind of enough, meaning that any transaction I send to it within 20 to 30 seconds, I can generate a proof and send it to Ethereum. Right? So TLDR is yes, you can do the privacy solutions on your home machine if you're tolerating this. Again, if you don't have a GPU, you can actually run it on CPU. This will take 2-3 minutes, but it's also workable. So yeah. But the point is that you don't need a cluster. You can just literally, for small set of transactions, you can do it right now at home.
And do you think industry will generally go in this way? Because looking at the other zk VMs like SP1 and RISC-0, that's kind of prover networks required at this point.
So that's the thing. I think that, yes, we'll be going, you've seen the speed, how we improve the performance of zk. This means that things that required clusters can now be run on single machines. My hope is that we might still need prover networks because just the amount of things will grow to be proven. But a single proof will not require 50 GPUs working in sync unless you really care about some crazy low, millisecond level latencies. But for normal use cases, if you're happy with a couple seconds, you should be fine with a single GPU. So yes, try the Airbender. Let me know how it works.
Amazing. Thank you so much. Let's give one more huge round of applause.